Good evening, guys.
Good evening, sir.
Have you guys practiced anything? Okay, now let's start. Let's understand some basics. As you already know this, but still, just want to explain. So before that, uh, how to find the deflection or rotation by using unit load method. If it is a axial load, then we know capital P into small p L divided by A E. If it is because of axial loads. What if it's because of bending moment? If it is a bar, let us say if we are talking about a bar, let us say if it is subjected to the axial force P. If you consider any section, what will be the axial force over the entire length of the bar? That I can say it as a P. But if I talk about a beam, and let us say it is subjected to some type of loading, what do you think the bending moment variation? Unlike the bar, bending moment might vary over the length of the beam. So, if you want to find out deflection or rotation, what you have to do? We have to use the integrals. Integral over the entire length, 0 to L. What we have to do? Capital M into small m into dx divided by E. Then, if you want to find out the deflection, what you have to? You have to apply a unit force. If you want to apply a slope, because of the forces, deflections will happen. If you want to get the rotation, obviously we have to apply unit. Let us discuss a simple case we are all aware of. Imagine this is truly vertical, even though it's not. There is a capital load P. Let us say the length is L. Let us say A, P. If I want to apply unit load method, can you tell me how we can apply? If you want to find the deflection at delta, that is nothing but an integral over capital M into small m into dx divided by E. Let us say EA is constant here. Now here, as we can see, there is a beam AB. If I assume that my section is from A to B to A, let us say I'm considering a section XX, that is the distance of X from the point B. Now can you tell me, at that point, what will be your bending moment? It is nothing but P into X, isn't it? Sign convention that we consider here, if you are talking about the deflections, it's up to you. If you are drawing a bending moment diagram, what is the sign convention that we have to follow? If there is sagging, then it is a positive. If it is a hogging, then we consider it as a negative. But coming to here, you can consider any direction, like you can consider clockwise as positive, or you can consider anti-clockwise as positive. At the end of the answer, ultimately we are finding the deflection, so it doesn't matter. If I consider clockwise as positive, then I will treat it as a plus X. Now, if I redraw the beam again, if I want to find out the deflection, as the load is horizontal, let us say I want to find out the horizontal deflection. As I want to find out the horizontal deflection, wherever I want to find, what I should do, I will apply a unit force here. I will remove the applied loads and I will apply unit force on whatever the direction I want to find the deflection. If I want to find the vertical deflection, I will apply a unit force in vertical direction. So it's about the direction also. Suppose let us say if I want to find out the deflection along this direction, then apply the unit load along the direction. So it's up to you. It's depending upon the point and the direction you are finding the deflection. As I'm interested in finding the horizontal deflection, that's how I'm applying the unit load along the horizontal. And then I'll consider the same section, let us section X from the support B. And then because of the unit load, what is the moment here? Again, it is a clockwise. So 1 into X plus X. So what about the deflection at B? That will be equal to integral over length of the beam is defined as 0 to L. Capital M is given as Px and small m is obtained as x dx divided by Pl. So obviously Px square. What is the integral of x square? X cubed by 3. If you apply the limits, then what is the final end of the equation will get? Pl cubed by 3. Now at the answer we are getting a positive value. What does this positive represents? So this positive represents that your deflection is along the direction of unit load. What is the direction of the unit load we have considered? Right side. So you can say that it's acting on the right side direction. So the same logic, but in comparison with trusses, in trusses we won't apply the integral part. Why? Because in trusses, so the forces in a member is constant, they won't change on the length. But in a beams, they will vary bending moment. So that's why we will apply. What if I want to ask you to find the vertical deflection? So instead of a horizontal load, what you will do? You will apply a vertical unit force. So if you apply a vertical unit force at any section XX, will there be any movement because of this force? It is an axial load. So small m will be equal to 0. That means if small m is equal to 0, then entire equation is 0. So that's why the vertical deflection is equal to 0. Now, what will be my rotation at point B? How can I find out my rotation? As I told you, if I want to find the deflection, I will apply unit force. If I want to find the rotation, then obviously I will apply the unit movement. Let us assume that I have applied an anti-clockwise movement here. Anti-clockwise unit movement. Let us say I am considering a section XX. Now, what will be your small m value? Can you tell me from this, if I consider section X, what will be the moment at this section? What will be the moment?
M only, sir.
M? What is the moment I have applied?
1, sir.
1.
Is it only 1? Direction also we have to take care, right? This capital M we have considered it as a clockwise. So here I applied the anti-clockwise. So what is the small m value?
-1.
You have to be very careful with this. Then what will be your deflection? Sorry, what will be your rotation at B? That will be is equal to integral 0 to L. Capital M is given as Px. Small m is given as -1 dx by dl. So what is integral of x? X square by 2. So if you substitute the limits, what you will get? Minus L square by 2E. Now what does this direction implies? What is the direction of the unit moment we have considered?
Anti-clockwise.
So this represents that opposite direction. So here PL square EL. Just oppose what I will consider.
Clockwise.
So it's just a direct application, right? Now, in the same way, there is a deflection. Sorry. Again, the same problem I am talking about. P, the length is L. What if I ask you to find the deflection at x equal to L by 2? L by 2 from fixed support. Let us say A, B. Can you quickly apply and tell me what is the deflection at point C? Obviously, I mean to say horizontal deflection at point C.
The PL cube by 24 EI, sir.
Capital M won't change, right? Only the change will occur in small m, isn't it?
0 to L by 2.
For small m, what is the section we are considering? We are considering section from B, isn't it? So where we have to apply unit load? First of all, we have to apply unit load at a distance of L by 2, isn't it? Now, if I am representing my x from here to here, then how can I simplify this? So what I should do? I should divide this in terms of two parts, right? If I consider from x from B, first I will consider in between the limits 0 less than x less than L by 2. Why? Because if you consider a section somewhere here, what is the moment? Small m. Unit load is presenting at C. What is the moment in between B to C? Are there any loads in between this portion? What is the small m in between this portion? 0. What about from L by 2 to L? What about your small m? If I consider a section somewhere around here, then the moment will be this much. So m will be 1 into x minus L by 2. Have you written like this only? Or have you written in some other way? Is this equation okay? Now I am applying the unit load here. I am considering a section from here. And this distance is L by 2. And this distance is L by 2. A, B, C. Now, in between B to C, what is the bending moment? Can you tell me? In between B to C, what is the bending moment? Do you agree that moment is equal to 0 or not? Look at from C. If you imagine like this, what is the bending moment in this portion? If you consider any section in between here, and if you look into the right side, are there any forces acting on the beam? No. Then what is the moment?
0.
That's what I'm writing here. To the upward of C or in between B. Are there any forces acting on that portion? No.
No,
There are no forces, that's why your moment is equal to 0. But if I consider a section somewhere around here, then obviously the moment will exist because of this unit load. So what is the moment? Load into perpendicular distance. What is the perpendicular distance? From here to here. We are representing x from point B. From here to here it is x. What is the distance from here to here? From here to here it is L by 2. So what is the distance? X minus L by 2. So because of the unit load, what is the moment? That is x minus L by 2. That too in the portion L by 2 less than x less than L. That means in between from L by 2 to L only, yes, in between x L by 2 to L only moment is existing. Now, how can I apply this equation? My deflection at point C, that will be equal to, how should I find out? That will be equal to, previously what we have done, we have integrated from 0 to L. Why? Because with single equation we can represent it. But here what is happening? Your small m is different from B to C and it is different from C to A. So what I should do? I should divide it from equation capital M into small m into dx divided by EI in the portion 0 to L by 2 plus I will obtain from again L by 2 to L capital M into small m into dx by EI. My capital M, I can define it by x, but what about small m? In between some portion, it is not existing. Whenever it is undefined, so obviously we have to split it. So in between this portion, what about your small m? 0. That means what about this entire value? 0. So only the remaining part is this. That will be equal to integral L by 2 to L. What about your capital M? E times x. What about your small m? Small m is defined as x minus L by 2 times dx divided by EI. Can you quickly tell me how much you are getting? Can you please do the calculation and tell me what is the value you are getting? If you can tell me, then we can go forward.
1 minute, sir. Calculating.
Yeah, thank you. Little bit least. Why it's taking so much? Okay, there might be some calculations. Okay, now keep it aside. Can you tell me what will be my deflection at C, rotation at C, what will be my deflection at B, and what will be my rotation at B? Leave that calculation apart. If you guys understood, that's fine. Now, can you tell me for this case, for this, can I use the standard case of this one? So first point you have to understand is that in this case, the bending moment will exist in which part? The bending moment will exist in part C
A to C.
to C. In B to C, there is no bending moment. If there is no bending moment, then here the deflected shape will be linear always. That means it won't deflect, it just move simply because of the connectivity at point C. Wherever there is a bending moment, there only you will get the deflected shape. Deflected shape means some circular curve shape. Now, if I look into the only part is AC, what will be my deflected shape? My deflected shape will be somewhere like this. And if I add the remaining part, as there is no load at CB, then it's just simply linear. That means this is what the connecting point. So whatever the slope at theta point C, and it will be constant throughout the length of the beam. That means I can say here is that my slope is at point B is equal to my slope is at point C. Just imagine that it is horizontal vertical initially. Because of the rotation at point C, that point will also rotate. Take a vertical pen at your hand and try to rotate with your hand. And whatever the deflected shape that you can see, that is what you will expect in the portion B to C. Now this is like a cantilever portion subjected to the point load. That means what is the deflection at point Z that I can say? PL cube by 3A. But instead here, what is the length? Length is defined as L by 2. L by 2 whole cube by 3EM. Now what about the rotation at point C? Cantilever subjected to end point load PL square. Now in this case, what is the difference? PL square by 2EM. Similarly, what is the slope at B? As there is no bending moment, the part BC will deflect in linearly. That means here it just rotate with respect to point C. Now, what will be your rotation at point B? Rotation at point B is also same as the rotation C. Now, can you tell me what about this deflection at point B? If I divide this entire part into two ways, from here to what is the deflection, this value? This deflection I can define as deflection at C. If this slope is theta C, what about this magnitude? From here to here, what is the length? L by 2. And the slope is theta C. Then what about this deflection? Theta C into L by 2. So, in the same way, I can say my deflection at point B, that is nothing but a deflection at point C plus rotation at that point times L by 2. So, finding deflection if the load is in between A to B, and then if they ask us at any other point, then the things are much easier. They don't make us much difficulty. Did you understand the difference here? If the point load is given and if you want to find out in between, then it will be somewhat difficult calculation part we have to do. But if the case is like this, then it is much simpler to do it. Right? Now, it's clear, right? What is the deflection? What is the rotation at C?
Yes, sir.
Now, so let's come back to this question. It will be difficult, right? Integration doing, and obviously for you, it's taken some time. But what is the another way that you can find the deflection at some point very much easily? How can I make it quick? What is the other method? You can apply the conjugate beam method also. If you use the conjugate beam method, I don't think it will take much time. If you draw the bending moment diagram, the bending moment diagram will be like this. And where you want to find the deflection, here you want to find the deflection. So take the moment with respect to this point, or find the moment at this point. Only you can see it is the trapezoidal load. If it is a trapezoidal load, I remember if it is a trapezoidal load, how to find the area under the curve? A plus B by 2 into H. And also for the trapezoid load, you guys have to remember the CZ2. It will make most of the problems will be easier. You know, for the rectangle that will be remembered for everybody. For triangle also will remember, and for trapezoid also you guys have to by heart, because For some problems, you have to take the moment. Even not only here, even in the soil mechanics also, there are some problems that you might need it. So always remember for trapezoidal case also. And for parabolic also, you need to remember. For parabolic, can you know what is the reflection? What is the area of this rectangle? Let us say this is B, this is H. What is the area?
E into H.
E into H. What about the centroid? Centroid
H
is
by 2.
or B by 2. Now divide this into half. If I divide this into half, whatever the area of each part, as I divided into each part, half
B
it
into
will be.
H.
Then what about the area?
2 times of
Add 1 to the denominator. If you add 1 to the denominator, then it will be 1/3 of H. Then what will be the remaining value? 2/3 of H. Isn't it? Always remember from the 0 side, it will be the larger value. So from here, it will be 2/3 of H, right? Now, if I do this in the form of 2-degree parabola, what will be the area? You add 1 to the denominator. If you add 1 to the denominator, how much it will be? 1/3 of BH. And then what about the other part? 2/3 of BH. If you can look at the areas, what do you think for the part 1 and for the part which is having the larger area by looking at the diagram itself?
1, sir.
By looking at the diagram itself, we can say for 2, the area is somewhat lesser. So for this, the area will be 1/3 of BH. For this, the area will be 2/3 of BH. And what will be the CG portions? Can you tell me the example where we have used this curve? Have you ever used this curve? Have you guys studied RCC?
Not yet, sir.
Have you ever used this shape of curve in RCC? This type of area, 2/3 of BH. What is the stress strength of for concrete? Right? Whatever the area of this part. And similarly, whatever the CGs, add 1 below, 1/4, 3/4. Okay. Now let's come back to our case. So it's just easy to remember. If you know one thing, everything can be correlated. That's what I meant to say. Add 1, add 1, add 1. So everything will be in the form of same way. Why? Because it's just integration part. Integration of 1 is how much? X. Integration of x is how much? X square by 2. Integration of x3 is how much? X cube by 3. So in the same way, if we can add 1 more degree to the previous case, the next case can be obtained easily. That's how here we can correlate and you guys can remember. That's not a big task. Now, P, length is L, the length is L, A, B, C. Now, I am interested in finding what is my horizontal deflection at B, what is my rotation at B, what will be my horizontal deflection at C, or I can say my vertical deflection at B, what is my rotation at C, what will be my vertical rotation at, so vertical deflection at C. Can you tell me how to solve this case? Don't be in a hurry to solve this case. First of all, understand the mechanism, how the load will transfer, and then tell me how can I find out these 6 values. If you look at this case, in BC, can you tell me, will there be, what if the axial force exists, what is the axial force? If the shear force exists, can you tell me what is the shear force? If bending moment exists, can you tell me what is the bending moment in the part BC? Which type of forces will act on the BC? Can you tell me?
Axial load, sir.
How much? What is the axial load taken by BC?
P, sir.
Huh?
P.
P. Is everybody will agree to it? Now, let us say I'm consider some section around here. Okay. Even for the axial load, can I say how to find the axial load at a point? How to find a bending moment at a point? Look at any one side and then add summation of moments, right? Similarly, if I consider this is my section, look into the right side and tell me, are there any axial forces acting on the right side?
No, sir.
What is the axial force at this section? What is the axial force at this section? Is it 0? Or let us say if I want to find the reactions at point A, the horizontal load is acting at point B, then obviously what will be the reaction here?
P, sir.
Even if you look into the left side, how many forces are there on the left side? P on the right side, P on the left side. If you add those two, how much you will get? BC is not carrying any type of load. What happens? The BC is just connected at point B only. It is not, because of its mechanism, it is not carrying any load. Let us say, if I keep a roller support here, will it carry any force? If I carry a roller support, will it carry any force?
No, sir.
No. If it is a single support, will it carry any force?
Yes, sir.
Yes. Now, let us discuss few things here. If I draw the free body diagram of AB and AC, AB and BC, if you look into the right side from B, no forces are acting on the BC. So that's why no axial force, no shear force, no bending moment. So what will happen? It just, if nothing, no force is acting, it just treat it like a rigid body. Whatever the force that is acting, that is resisted by the part AB only. Even though it looks like a frame, but because of the load arrangement, how it is looking like? It is like cantilever subjected to point load at the free end. What will be the deflected shape here? Can I say my deflected shape is like this? Now, what will be my deflection at point B? What is the deflection? Horizontal deflection. What is the horizontal deflection at point B? Can I say that is PL cube by 3A?
Yes, sir.
What is the rotation at B? Can I say in the formula PPL square by 2EA?
Yes, sir.
Obviously, the vertical deflection, I can treat it as a 0. But what is this joint here? Rigid joint. If you just remember, what is the conditions for rigid joint? Rotations of the members will be same, isn't it?
Yes, sir.
So at B, now how many members are connected? 2. AB, BA and BC. Whatever the slope at point B, that will be the slope for point C also. So if I draw the deflected shape here, how it will deflect like? Because of the horizontal load. From here to here we know. Let us say this is the point B. It has moved to the B dash. Now can you tell me how the BC will deflect? Whatever the angle between the numbers before the application of the load, 90 degrees. What do you think after the application of the members? Again, it will be 90 degrees. That means the rotation between the members will be same. As it is not resisted by any load, so the rotation at B or the member BC will rotate by the same amount at B. That means if I draw the reflected shape, the reflection will be like this. Here it is a some curvy shape as it is resisting the load. But if you look at the B dash and C dash, you can see it is just a linear line. Why? Because it is a linear line. As it is a rigid joint, the member BC is rotated by the amount of rotation. Now, if you find the angle between these two, the angle between these two will be 90 degrees only. Now, at point C, what is the horizontal deflection from here to here? Can you tell me? By this visualization, can you tell me what is the horizontal deflection? Point B has moved to how much? B dash. That implies C also have moved to C dash. So what is the distance between C to C dash? That is nothing but a B to B dash. What is the B to B dash? That is what nothing but a horizontal deflection at point B. What is the horizontal deflection at point B? That is PL cube by 3EL. Now can you find out what is this vertical deflection at point C? What is this magnitude from here to here? What is this value? Theta B. That implies what is this ordinate then? What is the vertical deflection at C? If this is deflected by like this, if this value is theta b, what will be this magnitude then? Theta b into length of the portion BC. So what is the vertical? So rotation at point B into length of the portion BC. What is the deflection at B? Rotation. PL square by 2A. What is the length of the portion BC? L. That implies how much? PL square by, PL cube by 2EI. Now, what will be my rotation at C? What will be my rotation at C? At point C. If you don't tell me rotation at points, that means you didn't understand this.
0, sir.
Is it horizontal member or it is member? Portion BC.
Horizontal members.
After the deflection, is it the horizontal member or the inclined member? It has become. If it truly
Become
horizontal inclined, then that means obviously the slope exists. What is that slope?
Same as the top theta.
Yeah. So the deflection at points or deflection at any point in BC. That is equal to deflection at point B. Did you understand the logic? If it is not carrying any or the member, if it does not have any moment, it will just, the reflected shape of the member will be linear. That means slope of the member will be constant everywhere.
Yes, sir.
Can you find out what is the horizontal deflection at point B? First of all, what can be the difference between this case and the previous case? The previous case is like this. What do you think the difference will become? If you can identify the difference, then I will be much happier. What is the difference that you can observe? Is both are same or they will be different? If they are different, I just want to know.
Different, sir.
Yeah, they are different. On what basis or where the effect will come because of this roller support?
In this vertical
Placement
deflection at
at
C.
As it is at the end, as the rotation is at point B, the deflection at point C is allowed, right? So that's
Yes,
why
sir.
it is. But here, what is happening because of the roller support? It won't allow any vertical deflection. That means, what about in the member BC? Will it deflect or it won't deflect? Just think about it. How can I proceed or how can I solve this?
Horizontal deflection will be there, sir.
Horizontal deflection at B will be, that is obvious. Horizontal deflection will be there. That's for true. But did you understood? If there is no joint at C, vertical deflection can happen at C. But
Yes.
because of this additional support, that is also restrained. If that is restrained, how the load path or how the load distribution can happen in the members? Imagine sequentially, if there is no support at C, it will behave like a cantilever, and then BC will be like a simple linear deflection or rigid body rotation will happen in the BC. Now, if I restrain this vertical deflection at point C, how the changes are gonna there? One thing I can say that here also it is horizontal. This is what I can say, right? Can I say this is P, isn't it? Now tell me here, what about the reactions? Here the reactions is also nothing but a P. And what about the vertical reaction? Will there be any vertical reaction here? In this case, will there be vertical reactions exist at point A? What about the vertical reaction at this point?
Yes, sir. It will be present, sir.
It will present. How much it will be? Any other reactions, any other supports are there in this section?
Sir,
In this case-
reaction at C, sir. Reaction at A and C will be equal and opposite.
In this case, what will be the reaction at A? Is there any support at C?
No, sir. In that case, it is 0, sir.
It is 0 though, so that's what I'm asking. It is 0. Now, come to this case. If there is no support, the deflection is possible, isn't it? If the deflection is possible, that means as I'm restraining it, definitely the reaction force will develop. If there is no support, this point is going to deflect in the downward direction. But this support is not allowing any deflection. That means obviously the resisting force will develop. Let us say this was the resisting force upward. As there are no other loads, as it is upward, so here obviously
Downward.
movement will also, some movement will generate here. How much it generate, that we can look into later on. Now the thing is, if I consider a section BC, what do you think about the forces, internal forces? Will they exist or not? What I mean to say is that bending moment will exist or not? Bending moment will come or not?
No load, so doesn't come, sir.
At this section, look into the right side. Any forces acting there?
No,
If you
sir,
look-
no.
What do you think because of this moment will develop here? Because of this load or because of this reaction or moment will develop or not at this section? Let us say if this section is X. Because of this reaction, what is the moment at this section?
R into X.
That means bending moment will develop.
Yes, sir.
Previously, if there is no support at C, there is no bending moment, there is no axial force, there is no shear force. But because of this addition of the supports, as you are restraining the vertical deflection at C, definitely the moment will develop and it no longer behaves as a rigid body.
So,
Now, the next thing I want to ask you is, how can I find out these values? What is the way to find out the values of this case? Is it determinate or indeterminate? So first of all, you have to use indeterminate methods to solve these problems. And then if you're using slope deflection methods, directly you will get the slopes. If you're using the moment distribution method, you will get the moments. And then based on them, you have to find out the values. So if you see the deflected shape of this case, it might be deflect somewhere around like this. Previously, see, if there is no restraint, it is just simply like this. Now in this case, the reflected shape will become like this. That's how the difference comes here. Now, let us further increase the complexity. In this case, how can I find out the values? How can I find out?
Load is acting only on BC members, sir.
How to find out vertical deflection at C, how to find vertical deflection at B, rotation at B, rotation at C. Yeah, you are saying something? Only?
Load acting only on BC members, sir. So we can treat like a cantilever.
Yeah. So after rotating like a cantilever, then my final, I just need you to find what will be my vertical deflection at point C. Is it PL cube by 3I? Or it's somewhere else? For this case, you can use unit load method, then also you can get the values, but finding unit load is easy. I don't think it makes it difficult, but if you don't want to use unit load method, but by using some other logic, can you somehow find out or not? That's what I'm interested in.
Can you use superimposition method?
Yeah. Now what is the, let us separate the members as usual, right? Here if it is P, now whatever the forces about this point, can you tell me? Whatever the forces here, forces will generate or not at this point? Can you tell me
Yes, sir.
whatever the vertical force, horizontal force and moment that develop here?
Upward vertical force, sir.
Upward vertical force, P,
Movement
whatever the
anti-clockwise.
moment
Anti-clockwise.
clockwise, whatever that magnitude, E, L. Now whatever the forces here, look at the joint. If you look in the initial,
Clockwise, sir.
are
Clockwise.
there any
movement.
forces? No. So it will be equal and opposite. So here it will be, if it is upward force, so here it will be downward force P. It is anti-clockwise. So here it will be clockwise
Clockwise.
to M. Let's say this is what the magnitude M. Now look at this case. Look at the part AB. If this is axially rigid, then obviously because of this P, it won't affect, isn't it?
Yes, sir.
Now, this case you can simply find out by remembering the formulas. I don't know whether you guys remembered or not. If there is a concentrated movement, what will be your
P-
deflection and what will be your rotation?
PL divided by AE.
If there is a cantilever with magnitude M, what will be your rotation at free
ML
end?
divided by 2EI
ML
divided by
rotation.
2EI. Rotation.
Is it ML divided by 2EI?
EI,
Or
EI,
simply
sir.
ML by EA?
Rotation EI. Rotation EI.
If it is a deflection,
MS square by 2EI.
right? Now you can see rotation, deflection. If it is a concentrated movement, what is the denominator that I'm talking about? 1. 1. What is the denominator? 2.
2.
If it is a point load, what is the rotation? PL square by 2A. What is the denominator? 2. What is the
2.
deflection?
3.
If it is UDL, what is this value and what is this value?
6, 12, 6, 24.
In this case also it is very much easier, right? So just everything you can relate like this, then you guys can remember everything well. Unlike remembering for the particular case, for movement, for point load, for UDL, try to correlate with the values, then you guys will be remembered without committing any mistake. Now, what will be the deflected shape for this portion AB? Again, it will be like this, right? Now, what will be here? There will be some rotational here, theta B. Now, if I add these two, how I am going to find out my deflection at point B? Now, let me go back to the previous case. If there is no load here, how we have told find deflection at point C? How we have won the deflection at point C? Deflection at point C is occurred due to vertical deflection is occurred due to what?
So, sulfite.
No, in this case, deflection at point C occurred due to what reason?
Phase.
If rotation at point B is equal to 0, what will be your vertical deflection at point C? If there is no rotation, the member will be truly horizontal even after the deflected shape. Because of this rotation only, you are finding this value. If there is no rotation, there is no deflection. You can see here, right? Because of this rotation only, you are taking it as inclined path and then you are taking the deflection. So, similarly, in this case, what is happening? I will ask you two things. In one case, there is somewhat load like this. And in another case, there is a load like this. So whatever the deflection at this point, that is happening due to what? Due to the rotation at point B. No other loads are acting here, right? That's why
Yes,
it is deflecting like a rigid body. That means simply linear. But what about in this case? Is this deflect like a rigid body? Or the moment is existing here?
Movement exists here, sir.
Movement is possible. So that's why,
Yes, sir.
because of this force, so if I want to talk about the deflection at this point C, again, two types of deflections are possible. One is because of what? Because of rotation at point B, and another is because of this load. So simply, if I want to find out my vertical deflection at point C, what I will say is that due to rotation at B plus due to loads in BC. Now, because of this rotation, what will be the deflection that is possible here? Forgot about this load first of all. If you forgot about this load, because of this rotation, how much deflection is possible at C? That is nothing but rotation at point B times length of the member BC plus because of this force. Now you can imagine if it is a cantilever subjected to point load, whatever the reaction here, upward, whatever the moment here, PL. Now can you correlate these two? Are they looking same or they are different?
Looking same, sir.
That means whatever the deflection at this point then, because of this load, that will be PLBC by 3EI. Here now we have found out this is ML by EI times length of the BC is L. So here also it is PL cube by 3A. Now we know what is the value of L? PL, L square, L cube. So here it is PL cube by EI plus PL cube by 3EI. So if I ask you to represent of the deflected shape, if I draw it, first what I will draw is that this is what the rotation C, and then the final deflection will be somewhere here. If I divide this portion from here to here, I will say that this is because of the load in the portion BC and this additional part because of the rotation. Any doubts in this case?
Clear,
So if
sir.
I look at this diagram entirely, then it might feel deflect, but if you visualize the things, then means two things. That is, that deflection at points that will occur because of this rotation and then because of this load. So if you remember this logic, then it will be good, more than enough. Now, suppose, how can I find out the things here now? What can be my deflection at C? What can be my, always my rotation at B? What can be my rotation at A? How can I get obtain here? Think in the same way. Can we obtain or not in the, or what are the cases we have discussed? Imagine there is a member here like this. It is just restant at this point only. Or imagine, let me make it as a determinant. How can I find out? If this is L and if this is L by 2, are you going to find it out? Can you simply say what will be the reactions? What can be the reactions at A and B? You guys,
Zero.
the total moment that act on this PL clockwise to opposite. Here it will be downward. Here it will be upward. Whatever those reactions, net moment by length. What is the net moment? PL by 2 by L. So here what is the magnitude? P by 2. And here what is the magnitude? P by 2. If I draw a free-body diagram, A, B, and B at C, this will be right side. And here it will be upward. And whatever this magnitude, L by 2, clockwise. So here it will be anti-clockwise. Here it is anti-clockwise. Here it will be clockwise. Whatever this magnitude, PL by 2. Let us consider the same supports. Now can you tell me what about my vertical horizontal deflection at point C? Previously, I have rotation will occur. Again, the rigid body rotation. I can say due to rotation at B plus due to load at P. What is the due to rotation at B? Because of the rotation at B times what about the length? L by 2 plus, again it will treat it like a cantilever. As you can see, if you draw cantilever, if you draw it, if there is a force P and if there is L by 2, what about the reactions here? P, and there is anti-clockwise movement PL by 2. So what is the deflection? PL cube by 3A. What is the length here? PL by 2 cube by 3A. I have given you the same thing, but in a different way. The thing is, here you have to find out theta B. So these cases also you have to find out. If there is a simply supported beam and if there is a moment acting here, what can be the rotation? Can you tell me what is the rotation here? If I given you the length and if I given you the EI, can you tell me what is the rotation possible here? The moment is acting here is how much? PL by 2. Can you tell me what is the rotation at point B? Think of moment distribution method. If you think of moment distribution method, think about the stiffness method and then you will get an idea. If R end is hinged, then what is the stiffness?
3 by L, sir.
3EI by L,
L.
isn't it? Now, so this is what the stiffness. Stiffness I can correlate it as M by theta.
Yes,
What
sir.
is my M acting at that point? P by 2.
PL
Then
by
what
2.
will be my stiffness then? M by
I
3I by L.
L.
So M is PL. L if I go to upstairs, PL square 2 times of 3. PL square by 6EA. So here what is the value? PL square by 6EA times L by 2 plus PL by 2 cube by 3 over. The same thing I have given you, but I have reversed the frame. Ideology is same. Is it okay?
Yes, sir.
Are we discussing anything? We are not discussing anything new, right? That's what I mean to say. We are just thinking in a different perspective instead of going in a traditional way of doing these cases. These cases, you can, if you did not strike these things, you can apply the unit load and then you can find out the deflections, or you can apply, you can use the conjugate beam method, or you can remember what are the method you can apply. But the thing is, at the end of the day, you have to get the answer. There are two things. Either you can do it fastly or you can do it slowly. That's what the matters. So there is some smart way of doing. That's what you guys have to remember. Now, what is Betti's theorem or Betti's reciprocal theorem? If there are two different set of loads, let us say at first I have load applied at 1, let us say P1 and P2. And what I did is that I have measured the deflections at this point, let us say delta 3. Here it is, let us say delta 4. In the second case, what we have to do? In the second case, I'm applying the forces at sections 3 and 4. Let us say P3 and P4. Now, because of these loads, we are finding the deflections here. Let us say here the deflection is delta 1 and here the deflection is delta 2. According to the reciprocal theorem, this load and second load deflection, this load and second load deflection. That means what I can say? Load in first case, P1. What is the deflection at that section due to second case? Delta 1 plus load in first case, deflection along the direction in the second case. That can be written as a opposite P3 into delta 3 plus B4 into delta 4. The point is why this is useful, right? Can we just do the simple application of this method? Now, case previously, right? What is it? Let us say this is P. I have asked you to find the deflection at point C, right? How much time it took to solve this case? Did you remember? Just now we have solved it by using unit load method. I don't know. Did you get the final answer for this case? What is the deflection at C? Okay, leave it. At least tell me, is it simpler if you are using by a unit load method? Is it simple to solve this? Find the deflection at C.
No, sir.
Right. Now, let me make it easier for you by using reciprocal shear. Okay. Now, what I do, let us say that what will be the deflected shape? I am drawing an enlarged shape so that you guys can understand. Right. I am applying the load here and I am applying the deflection here. Let us say what this is, delta C, isn't it? Now, what I do in the second case, I will apply the same load at point C. I will apply the same load at point C. And what I will do, I will measure the deflection at 3M. Let us say this is delta B. Can I apply a reciprocal theorem for this case? If you use the reciprocal theorem, can you tell me what is the equation that you will get it? Please, at least you can tell me. What load in first? Yes. P.
P into delta B plus P into delta C.
Deflection in the second case, delta B. That will be equal to load in the second case, here it is also P. If PP gets cancelled, then what I can say? I can say that delta B is equal to delta C. Can I say it?
Yes, sir.
Now, I'm telling you that this is L by 2, this is L by 2, A, B, C. Can you quickly tell me what is my deflection at point C here? Here, sorry. If this is C, that means this is C, this is B, right? Yeah. Can you tell me what is the deflection here? For this, you don't need to solve anything. Quickly, you guys can tell me. Now, you guys have to tell me what is the deflection here.
68 delta guys, sir.
Because of this load, what is the deflection here? If I simply do it, this what is the deflection from here to here? P into L by 2.
PSU by 2EI.
P
L by
that's what is the rotation at this point? P
Delta C.
L by 2 square by 2EI times L by 2.
Yes.
How much time it took to? That means this deflection is nothing but this deflection. Now, previously, if you're using unit load method, how much integrations you have done? You have taken the two different sections and you're applying. Now, hardly can you tell me how much time it will take to solve this case? Now you can tell me, is it easy or difficult?
EC, sir.
Better, right? I don't, it will be easier. Now you guys can understand what is the, if you apply some concepts, how the things might get easier. Clear? Can I give you one more case? Now, sometimes what you guys have to do is that, can you apply the reciprocal theorem here? If you apply the reciprocal theorem, can you tell me what is the equation that you can write? Apply the reciprocal theorem, just now you guys have did, right? Can you tell me what you can write here?
P into theta 2.
P into?
Theta 2.
What are the two cases that we are discussing about? P, and we are taking another section as here. What is the first case? P. And second case, you have to consider theta 2. So P into theta 2. That will be equal to. Consider the load in the second case. M.
M
And
into del 1.
second case. Isn't it? Now, sometimes if you have forgot M into delta 1, right? P into theta 2, yeah, that will be equal to. If there is a point load, you can find out delta 1, if that can be remembered. But if you somehow forgot, because of this M, how much rotation you can occur, then you can use this relation too. Can you tell me what is this value you will get here? We have written something on M into what you have to write here? Sorry.
M into del 1, sir.
M into del 1 only, right on. So this can be useful when, just like we have forgot, if I apply a moment now, you didn't strike how what is the rotation that you get here. But if you know this case, P and delta, then in the same way, if it is a point load, you know what is the deflection? Simply supported when subjected to point load. Deflection due to simply supported due to point load, central point load.
WLQ by 48 EI, sir.
48 EA. Now, you are having some moment, you don't know how to get this moment. Then in that case also, you can simply apply this equation. You can get the value of rotation too. So whenever you forgot some standard cases, or just like, let us say if they ask you given this case, or let me tell you one more thing. Let us say if this is M1, and here if I'm applying M2, theta 2, theta 1. Again the same relation, can you tell me? M1 into theta 1, theta 2, that can be correlated as a M2 into theta 1. So whenever you forgot some standard cases, by using this theorem, you can reproduce them and then you can find it out. right? Now let us talk about, if you talk about strain energy, already we have used the strain energy principles, but without knowing the applications of them. So if you talk about this strain energy, then simply we can say this as the internal energy stored in the member. Because of the load, obviously the member will deform because of the deformation. How much energy it has stored. That's what we have to find out. I don't know whether you guys remember this or not. Because of the load, what is the strain energy? P square L by 2AE. Have you ever wondered why this half has come? Even if you
The
draw the
area
yeah, area under this curve, that's why
half into P into delta.
delta off into P into delta. So the logic here is that whatever the problem that you are solving, let us say if this is load P, that means whatever the load, let us say if I talk about horizontal axis as T, at time T equal to 0, what is the load acting on the system? 0. As this time keep on increasing, after some period of time, let us say T1, the load is applying as how much? P. Let us forget it is P versus delta. Let us take this as a time versus force. At time T equal to 0, what is the force? 0. Up to certain time T1, there is a load of P. What does it we can understand here? Whatever the load that we are acting, they are not instantly applied. Instantly applied means if this is T and if this is P, instantly applied means at time T equal to 0, the complete load is applied. If they are gradually applied, that means we have taken some time. That means gradually we are increasing. Initially it is 0. If the total load is acting as 50, initially we have applied 0, then 10, 20, 30, 40, 50. Like that we are gradually increased. So whatever the deflection equations, whatever the things we are finding, all those things are due to because of the gradual loadings only. The point is why for gradual loading is that if you go into the masses, there will be effect called dynamic effect, or there is a called inertia effect. So if you apply linear load suddenly, inertia is coming going to picture. Let's like if suddenly if someone applied, if you are moving on a bus, if brakes are applied suddenly, what will happen? Due to inertia, we are going into the forward direction. So due to the or to neglect the inertial effects, you are gonna get the effect of mass will also come into the picture. To reduce that, we are slowly increasing the loads. That means whenever you are talking about the gradual loads, that means we are talking about the static loads only. Have you ever taken bridge engineering course? If you take a bridge engineering course, there are some terms called factors, impact factors. So their impact factors will be studied. Why? Because of the this inertial effect. The what are the deflections that are going to come? There will be much longer, much larger than due to the static loads. So to consider those effects, I don't know whether you guys taken or not. So there you will study about the impact factors because of the particular type of the load. So that's why the factor half comes into the picture because we are studying about the static load cases only. Have you ever walked on the bridge or a flyover? Have you ever walked on the bridge? Have you ever felt the vibrations there? Have you ever felt it?
Yes, sir.
So those are nothing but the inertial effects only. That means they are oscillating. So whenever the inertial effects will come, the things will oscillate. If you are talking about static loads, things won't oscillate, right? And then the first theorem of Castiglione theorem, what will say? If you differentiate with respect to the force, you will get the deflection. So if you partially differentiate it, with respect to P2, 2 gets cancelled. So how much will get? Capital P, PL by EA. So this is what nothing but your Castiglione's first theorem. And if you take this small p equal to 1, that is what we are talking about the unit load method. So unit load method is nothing but a subderivative of the Castiglione's first theorem. And if you're talking about second theorem, then partial differentiate with respect to delta, then you will get it as a force. So other than things don't go beyond it, it will be waste on time. What are the things that are required? We have already studied here. Okay, I think we have covered, we have taken ample of time, and then we have discussed what are the things that are possible. And still you guys felt something difficulty while practicing, feel free to message me and I'll definitely reply you. Okay.
Yes, sir.
What are the things you guys have discussed? If you can understand them, then that is more than enough. I don't think more than this you guys will require anything.
Okay.
Definitely, if you guys feel anything to discuss, let me know. Definitely, I will arrange a class and we will discuss there too. Or send a message to me, we'll discuss. Okay.
Yes, sir.
Yeah,
Okay,
guys.
Yes, sir.
Thank you, guys. Thank you for your cooperation. Thank you.
Thank you. Thank you, sir.
Thank
Thank
you very
you
much,
so much,
sir.
sir.
Thank you very much.
Thank you, sir, so much, sir.
Bye. Have a good day.
Bye.
Bye.
Thank you.